Welcome to this chapter where we are talking about Lenz's law. Just a quick recap about this law. When you have a change in magnetic flux, a coil can react to it in such a way that it will try to undo the change that is happening. In easier to understand terms, we've discussed that if you have an increase in flux, a coil will try to respond in such a way that it causes another magnetic field that repels the original magnetic field that is changing in flux. The opposite is true. If there is a decrease in flux, the coil will try to create a magnetic field that tries to attract it to undo that change. Now, the first question that is asked here is, will any of these situations lead to an induced current that we have in exercise 3? In the first example, example A, you start twisting, as seen at the top here, the coil, the surface, inside of a homogeneous magnetic field. Now, just to quickly recap, if we have to write down the equation that lets us calculate flux, it would be, well, first of all, the number of coils given by number n. That technically doesn't change very often, so it's hard to manipulate that one. The magnitude of the magnetic field that is going through the surface, and of course the size of the surface as well. Now, all of this, you take into account the angle between the perpendicular line onto the surface and the actual field line. So if you just start changing the angle, you will also get a change in magnetic flux, which is exactly what's happening here. When these two are lined up, meaning they are parallel to each other, the flux will be zero. As this thing starts rotating, you will get an increase in magnetic flux until the circle, the coil, would be perfectly perpendicular to the magnetic field lines, in which case it would be at its max. As soon as it turns past that point, however, you will get a steady decrease until it is again parallel to the field lines. So this will create a constant positive followed by negative voltage inside of your coil, and as a result, if that coil is closed, you will get current going one way and then the other in the next 180 degrees of the turn. This situation is where you just move your, well, it's not exactly a coil, but your surface inside of a homogeneous field along the field lines. This doesn't cause any changes in the number of coils in it. This does not cause any changes in the strength of the magnetic field, the magnitude of the magnetic field. And the surface stays the same. Why doesn't it cause any change in magnetic field? Well, it's a homogeneous field, so this would not lead to any sort of induced voltage or induced current. If we take a coil and we have a magnet nearby and we move the coil, you would also change the magnitude of the magnetic field line field inside of that coil. You would get a decrease in flux, which means this one will actually be good to go. So to recap, the first one is a change in angle. So that's good. That will lead to the induced voltage. This one is no change in your magnetic field and no change in your angle. So this will not lead to anything. And this will lead to a change in your magnetic field strength as you move it away, the magnitude of that field. It doesn't matter if you move your magnet or the coil, it would lead to the exact same thing, which is what we try to show in this next exercise. If you have a coil and you move that coil towards your magnet, you will get an increase in flux in this situation. An increase in flux means the reaction can be described as trying to repel it, right? Now, trying to repel it means the coil would try to create a magnetic field in such a way that the North Pole is on the right. If we then use the second right-hand rule to determine the sense of this current, you stretch out your thumb, your four fingers, your fingernails will indicate, in this case, the sense of the current. This means the current is going this bit from left to right. Now, if we move the magnet towards the coil, which is the situation C, again, you would create an increase in flux in these two situations, meaning it will try to repel, creating a south pole on the left and a north pole on the right. Of course, this means that if this is a closed coil, you will get a reversal of the current in this case. In situation B, however, and D at the same time, they are removing the coil and they are removing the magnet, meaning in these situations, both B and D, you get a decrease in flux. And the technical way to remember this is that it would create a field that would cause an attraction in this case, meaning in situation B, the south pole would be on the right side of the coil, like this. And in situation D, it would be the opposite. It would try to create a north pole on this end and a south pole, of course, on the other. We've already drawn these out using our right-hand rule, and that would lead to these situations. Now, in exercise 5, you've got a coil moving into a magnetic field at a constant speed, and you're supposed to draw the induced voltage in this situation. Now, it depends on how you look at it, of course, and how you connect your voltage meter, but let us assume that an increase in flux would cause a positive voltage, while a decrease in flux would cause a negative one. As this surface is moving towards the magnetic field, the first part of it, there would be no change in flux whatsoever. There is no magnetic field, so you can't expect any induced voltage. As it moves in, however, you create an increase in magnetic flux. And if we assume this means a positive voltage, you will get a slight spike upwards, until this whole block, this whole surface, is inside of the magnetic field. So moving from here to here, there would be no change in it. Why? Well, it is moving alongside a homogeneous magnetic field, and that doesn't cause any changes. Until, of course, it is ready to move out of the field again, you would create a decrease in your magnetic flux, and you would get sort of the opposite voltage compared to the first length of it moving in, followed, of course, by no change at all once it is completely out of it. So this was the first introduction video for these exercises. In the next video, we will study how you can actually practically use this induced voltage and how we can create electrical energy using movements, rotations, and all of that in a more practical manner. I will see you then.